Hi, I'm Cosmin, and I thank the organizer for giving me the opportunity to talk about BD algebras and group cohomology. So, in the first section, we recall what should be a Beilinson-Drinfeld algebra. In the second section, we talk about group cohomology, and we obtain as DG-algebras. And in the third section, we apply second section to obtain BD operators in the context of group cohomology. So for obtaining BD algebras, we use the general framework of BDR algebras. We take R to be a non-negative integer and K is a field. Recall that BV algebras, Batalin Vilkovisky algebras, are Gerstenhaber algebras equipped with a differential operator, decreasing of degree -1. And together with the product can express the Gerstenhaber bracket. For example, Hochschild cohomology of finite group algebras are cases of BV algebras. And there is now a recent paper of Benson, Kessar, and Linkelman where they explicitly compute BV operators. Now, BD algebras are similar to BV algebras, but the operator is increasing with degree +1. We can recover both structures under the name which we use in this paper, BDR algebras, by using the R Batalin Vilkovisky algebras, which appears in a survey of Cataneo, Fiorenza, and Longoni, and a change of indexing due to Costello and Villian. We change -R as a degree by 1 - R. So a BDR algebra is a triple H star with a multiplication and a bracket, so where H star is a Z-graded K vector space together with an operator delta BDR of degree 1 - R. So it goes from H star to H star plus 1 - R, such that there is a graded commutative algebra with a multiplication. H star shifted by L - 1 is a Lie algebra with a Lie bracket of degree 1 - R. The Poisson identity is satisfied. Delta composed with delta is 0, so it is a differential. And the Lie bracket expresses the failure of delta BDR of being a derivation. The first three items, actually, if we take R to be 2, we obtain the Gerstenhaber algebra. Now, if R is 0, we obtain BD0 algebra, which is in fact, what we call in this paper a BD algebra in the sense of Costello and Villian. If R is 2, we obtain BD2 algebra, which is precisely a Batalin Vilkovisky algebra, or one Batalin Vilkovisky algebra in Cataneo, Fiorenza, and Longoni. Now, our main objective is to use group cohomology and connective homomorphisms to obtain BD algebras. We take J to be a finite group, K a commutative ring, N is a non-negative integer, and A and B for the beginning are KG modules. There is the co-boundary differential, which we denote by partial A, which is used to obtain the classical definition of the group cohomology. So the N cohomology of G with coefficients in A is the N cocycles modulo N co-boundaries. If we have a short exact sequence of KG modules, like here, starts in A and ends in A, by using diagram chasing, and we take R to be the inverse, a map from the kernel of P into A, the inverse of iota prime, which is the isomorphism from A into the image of iota, and we take S to be a section of P, a right inverse as set maps, as maps of sets of P, then we can define the connecting homomorphism, which we denote by theta GA from the N cohomology into the N+1 cohomology. And this is defined by taking the cohomology class of phi bar mapped to the cohomology class of theta G A of phi. And theta G A of phi is obtained as R composed with a partial B applied on S composed to the N cocycle. Now, with some condition on A, B, the kernel R and S, we can obtain that the group cohomology with the crop product and the above map theta GA is a differential graded algebra. Now, in order to obtain BD operators and the structure of BD algebra, we assume that AB are K algebras with G acting by automorphism on A, P is like above, and S again is a section. But also we assume that K of P is an ideal of B. We take X to be an element in G, and then we assume two cases, that we have a consistent number of assumptions. So we assume in the first part that either there is a short X-axis sequence of KG modules of this form, which starts in A and ends in A, and iota index X is the injective homomorphism, such that if we denote by Rx the inverse of iota prime X, the above conditions on Rx-PS are true. And there is also a commutative diagram which assures us that the connected homomorphism which we obtain is a differential. So this is the reason for this commutative diagram. Or if it's not the case, if it's not the first case, then we by convention take Rx to be 0, such that we have a connection between all these maps. RYZ minus RY minus RZ is the restriction of KG homomorphism from B to the kernel of P. If these are the conditions are satisfied, we obtain the main theorem with the above assumptions. We take K to be a field such that A inherits a K algebra structure with J acting by K automorphism on A. And in this case, for any X in G, there is a K-linear connective homomorphism theta GAX such that the group cohomology with the cup product and with theta GAX is a DG-algebra. And moreover, the main part, if G is abelian, and for any X in G, theta GAX is also a K vector space map, then the group algebra KG, tensor product with the group cohomology, has a multiplication, a Lie bracket, and an operator which gives a BD algebra structure. Now, the multiplication is term by term. The Lie bracket for the BD operators is increasing of degree +1. So remember that in this case, R is 0 if we use BDR algebra. And it is defined by taking a pair into XY tensor product -1 to n theta with respect to y apply on phi bar, K product C bar, plus phi bar K product theta GAX applied on C bar. The BD operator is again of degree +1, so it's increasing with degree +1, and theta BD applied on X tensor product phi bar is X tensor product theta GAX on phi bar. We also have examples, a small example, where we take K to be the integers, G the cyclic group of order 3 generated by X, and capital K is the field with 3 elements. And the short X-axis sequence in these examples look like this, where P is a map, a surjective map projection, and Rx maps 3a plus 9z into a plus 3z, and Rx squared maps 3a plus 9z into minus a plus 3z. We need to have these maps, and these maps satisfies the above assumptions. Okay, and the references which we used are these. Thank you.